Yeah, okay. Yeah, it's
No?
no, it's on. Yeah, but it's off. Okay. Just quick. It's off.
Maybe no. Yeah.
It's fine, yeah.
Okay, let me go back. So yeah, for different ages, okay, or for different masses, we can try to develop a spectral sequence, which will be corresponding to temperature sequence. You know, so with decreasing temperature, we can try to see how the shape of the spectrum, this is in the near infrared, will change. And in these two figures, the example contain the L-type dwarfs, which have temperatures below 2000, roughly up to 1000 Kelvin. Then the T-dwarfs, where the main feature is the strong methane absorption, which is coming into play in the spectra. And at the bottom, the late T-dwarfs, which spectra looks like this, like a more or less like peaked emission in the infrared, which is mostly blocked by methane and also water vapor. Okay. And well, here today I will be focusing mostly on the coldest examples, so the Y-type brown dwarfs with temperatures below 500 kelvins. And here, well, the sequence that we have as for today, on the left side, a spectral sequence from late Ts to early Y types, or Y1 up to Y2. And well, you can see that the spectra are quite simple. No, there is not many features that we can see, only like a small peaked emissions along different spectral types. And in fact, the characteristic that distinguish them from the latest Ts and how they were defined roughly 10 years ago, it's simply that this peak, the peak in the J band flux, is getting even more narrow compared to previous one. I hope that you can notice, no? But this is the only feature, let's say, that makes them distinct from the previous spectral type. And also, the ratio between the two peaks here is changing. Okay. And what's responsible for this, let's say, shape? It's mostly occurrence of methane in the atmosphere, which blocks out most of the flux, and also ammonia that is started to be influencing the spectrum. And this was actually the best that we could do for this object for quite many years before the James Webb came into play. They were simply too faint and too dim and too difficult to observe, to get better observations. So here is one of the best, I think, observations available for a white dwarf before JWST. You can see as spectra right here. In the near infrared, this is coming from the Hubble observations using 15 hours of integration time, only to get this little emission and a few photometric points that could be measured. So there's WISE, 2 filters, and Spitzer observations. And that was it. They were simply too faint to do anything more until James Webb was available. And to tell you why this instrument is a perfect tool to study these objects, here is one example spectra of Y-type brown dwarf, roughly 450 kelvins. We could finally get a full SED and emission of this object in the peak region around 4-5 microns. Yeah, so before we could only see this and very, very hard. And now we can measure all these details and see how the spectral shape, and that is resembling the atmosphere, and study all the elements and different molecules that are occurring there in the atmosphere. Yeah, so now going back to our target for today, the accident. It was first discovered in 2020, so not so long ago. Here you can see the discovery images, which were WISE W2, and in fact the source was originally spotted in some sense by chance by an amateur astronomer who was working in the Backyard World's Planet 9 project, and he spotted this this little source here. What you can see, like a bunch of brighter pixels just above the background, moving along the background stars. And these are images taken over roughly 9 years, from 2010. And so that the object was selected directly from measuring its high proper motion. So no photometric colors were involved, no other measurements, just that we knew that it's moving. Okay. And here's some further follow-up observations that were attempted by that time. Well, despite the WISE W2 and W1 that are here in the corner, we have also Spitzer. Well, in the Spitzer data, it's detected quite well. Here you can see it right here in the circle. The circles correspond to different observation networks where we expect the source to be located. So, okay, we had detection in WISE W2, which is here and here, and Spitzer in the two channels, here and here. And the rest that is shown here were non-detections. Then, later on, it was tried with the Keck, but non-detection as well. With Hubble, it was possible to get the detection, and it's shown here. And then they also tried to obtain the J-band with Gemini after 10 hours. So they claimed to detect the source, but it was quite tricky due to background galaxy that was overlapping in this particular spot at that observing epoch. But after some subtractions and so, you can say it's a detection at the limit. So it's J-band of this object is 24.5. So 10 hours of 8-meter telescope time had to be spent to get a marked detection of this object. And here just to list all the measurements that were available before the JWST. Okay, so several detections, mostly from space. In the infrared, in the optical is totally invisible, so you can forget. And several upper limits. But despite that, we had only just a few photometric detections. Quite a lot could be measured, and we could tell quite a lot about this source even at that time. So from the proper motion, we could say that it's moving very fast, over 2,600 milli-arcseconds per year. So very fast-moving object. And most importantly, we were able to get the parallax and the distance of the object. So it was found to be located at 16 parsecs away. Okay. And then from the motion and the distance, we get the tangential velocity, which you can see is also very high, above 200 kilometers per second. So this would mean that most likely it is belonging to galactic halo population. Okay, from this kinematic. So this would mean that we have an object located in our neighborhood, 16 parsecs away, but it's a halo object. Okay. So now how it compared to like regular brown dwarfs. So looking at a photometric sequence of typical objects of this type, of the latest L and T type brown dwarfs, you can see color diagrams, bringing all the known sources here, and absolute magnitude color relation. And you see that the objects follow quite well-defined sequence here. Here we are going in that direction. You go to later types and lower temperatures. Okay, here are the known white dwarfs. Here are the latest T's. This green extreme point is the coldest brown dwarf known today. No. It's WISE 0855. It's also at 2 parsecs. Yes. 250 Kelvin temperature. But they all seem to follow, no? To follow the sequence in the colors and in the temperature. And when we try to compare the accident with this, it lies over here. So right on the spot of where it's totally empty, no man's land. So it's either too blue, if we would consider to be from this part of the population, or it's very much underluminous compared to the others. So okay, so it's either too blue or too faint. Well, just to tell this simply, it's just not fitting any kind of sequence of this object at all. So it's like totally out of sight. So at first it was quite a puzzling object, and we did not know what it actually could be. It was one of the possibilities that it could be a very old and low metallicity substellar object passing nearby, because somehow it fits to the predictions of models with low metallicity content of these objects. But still, it was rather unknown how it should behave in terms of photometric colors. We were just also starting to discover other examples of metal poor T dwarfs, and they are lying more or less in this region here. So above the overall sequence, but still not as extreme as this one. So several possible identities were discussed what this object actually could be in the original paper. So the authors considered several possibilities, like in fact, extremely young and low mass brown dwarf, or an ejected exoplanet, or a very old white dwarf, or these other more exotic possibilities, exotic stuff. But as discussed, and they were rather not so feasible and not so probable, in fact. So for example, for an ejected exoplanet, I think that people doing microlensing here, the experts know now that we don't see a big population of such objects in the galactic halo. Yeah, if I'm wrong, you can of course correct me, but I think the unbound planets that are found from microlensing statistics, they are found not to be so massive, no? So not having like tens of Jupiter mass. They are rather smaller objects. Or in case of a white dwarf, it will be simply not possible to cool down to these temperatures, given the age of the Milky Way. And then the one remaining possibilities was that it is a very old and extremely metal-poor brown dwarf. So here, let's say the model predictions, which are still at a very, I would say, low level of accuracy, are going in the right way where the object was measured to be. And also the high tangential velocity was suggesting that it is most likely a membership of an old halo population. But that was everything that could be done in the study of this source until it was possible to use the James Webb to obtain the observations. And we asked to do a program targeting this object. We asked for, I think, basically everything that we could get. We did near spec, low resolution and high resolution spectroscopy, MIRI spectrophotometry, and after 7-8 hours of observation, we get to what we wanted. No? So I would like to show you now the results. So that is the beautiful results for today. The full spectra covering the near infrared from roughly 1 micron up to
Please unmute your mic again.
maybe no.
Fine.
Okay. Yeah. So in the red is our target. In the green curve is a spectra of a 500 Kelvin brown dwarf. So something that is well, at least in terms of temperature, we should expect it to be similar. And in the pink, it's the coldest known brown dwarf, which has 250 kelvins. But as you can see easily, our target is also completely different than those kind of objects, the other white dwarfs. So in the near infrared, the flux is very, very much suppressed compared to let's say normal ones. And the longer, redder part in the mid-infrared at 5 microns is also totally different than others. So from the photometric colors, we already expected it to be significantly different. But yeah, to someone who was familiar with this kind of spectra, this was totally off the grid. So first, we tried to understand a little bit more about spectral morphology. The high-resolution spectra allowed to measure, to determine the radial velocity, which was necessary to confirm whether it's really belonging to the halo or probably not. And here in this diagram, you can see a comparison with different galactic populations. So the thin disk and thick disk in this range here, the blue and black, for non-Gaia stars, and halo with larger velocities and kinematics of our target. It is located right here. So we can easily and with high confidence say that it is belonging to the halo population. And yeah, coming back to the spectra, so we tried to understand more what is happening. At this point, we don't have available any theoretical models of these low temperature objects at this level of metallicity. Maybe minus 0.5, minus 1 is the most that was computed so far. And this was still too low to even try to compare the, let's say, standard classical models of brown dwarfs to these observations. So in this work, we did not even try to fit the full spectra that we obtained, but we tried to understand a bit more about what features do we see here and what features we don't see. So the two spectra are low resolution and high resolution, shifted just for the display. And apart from the overall shape, you can see not so many features in here. So absorption lines, here, something here, and here. And you can notice that they are, and this is not noise, this is something real, no? Because you can see it in both observations. But not so many, no? We have some lines here, some lines here. So this we know already that this is coming from methane, prominent absorption feature from methane and water bands. Yeah, water vapor absorption here. And then we notice that there is something here and something here. So at first we thought that one of these could be related to the phosphine, now quite famous compound because of the Venus observations. And this band here, this absorption line here, was quite a mystery at the beginning. We did not know what it could be causing this. And we did not, in fact, we did not expect any absorption to be happening in this particular wavelength. But yeah, we attempted to figure out what could be causing this, and how it was done. To simply present this to you, what we did is try to compare for different molecules that could be expected to be present at these temperatures in the atmosphere. We compared to something that is called cross sections of certain molecules or atoms, and tried to see the transmission curve, or that is how given molecule blocks the flux. No? So here an example of methane, quite well understood. You can see easily that here we could expect absorption feature, no, in the spectra here. So it should translate into our observations, and we can see it clearly here. So it's done more or less like this, and here in this case, it's quite easy. We did not see something that we could expect, that is carbon monoxide and carbon dioxide. It should be present in these regions where we should see also strong and broad absorption. In this picture, we don't see it at all, which was one of let's say, many surprises here. It's simply not there. We could also tell that there are no phosphines here. We considered this as one possibility at the beginning, but we figure out that it's not there, because in that case we should see a strong feature here in this part. So that was not it. And then we tried to consider another possibility, which was deuterated methane. And here you can see also the cross-section curve on the top. So it has a feature here and an absorption here. So quite close to our position here. But at the end, it's not well aligned. When you compare, let's say, draw a straight line here, you will see that it is shifted still to the left. So even from that, you can tell that it is not corresponding to this compound. Plus, we would not expect deuterium to be present in this object. Well, simply because it's too massive. It's not a planetary mass object, so the deuterium is definitely depleted here. So after checking various possibilities that are included here in this colorful plot, we finally found a good candidate, we think, which is the silane molecule. So silicon and hydrogen compound. So as you can see here in this comparison plot, it has a quite strong feature, right exactly on the spot on the 4.56 more or less microns, where we wanted it to be. No? So it's just a single line, okay? We see just a single feature, but it fits pretty well with the, let's say, what we would expect from this molecule. So that is our let's say main conclusion and main discovery of at this point, that we could detect the presence of this like silicate version of methane. Okay, let's say. Yeah, because instead of carbon, you have silane. You have silicate. So it was quite surprising, because we did not see this molecule at any object before. I mean, any brown dwarf that was observed, or even we do not see this in the solar system, for example, in Jupiter. This molecule is not seen. Okay. So now let's say the puzzle was to give some idea why and how we would be able to get this molecule seen in this object. Okay. So we tried to do some simple chemistry calculations and retrieval models to try to answer this. And we find out that it is indeed possible in that case when we have a metal poor environment. So when I mentioned Jupiter, for example, where the temperature is even lower, okay, we still know that the silicon should be present there, but we don't see it, no? And any probe that has studied the atmosphere did not detect this molecule there. But why? Well, we think that because of the higher metallicity. And in that case, the silicon can can be bound to other metals, most likely oxygen and magnesium. And in that form, it forms heavier grains of condensation, which sink down to deeper layers of atmosphere, which could not be seen. And in our case, in the case of accident, because it is a very metal-poor object, we actually don't have enough heavier elements to combine with silicon. And there is enough silicon left to be joined with hydrogen. So therefore, we can see like a quite high abundance of it in the upper parts of the atmosphere still, because it is a lighter compound. As well, it can tell us something more about the structure of the atmosphere and the processes that are occurring at the deeper layers. Because in that case, to be able to observe it at the levels we are seeing it, it would have to be mixed from the deeper layers still. So in that case, at higher gravities, it had to be mixed to a turbulent vertical mixing in the atmosphere and quenched from the deeper layers to the top. Okay, and since this is old and a massive object with quite high surface gravity, we think that the scale height and the rate of the vertical mixing could enhance the abundance of this molecule. Okay, so going further with that, we could verify that the metallicity is indeed very low. We obtained a value of -2, so about less than 1% of the solar abundance, and we determined the carbon-oxygen ratio. And when you compare these values to FGK stars in the disk, in this region here, and in the halo, okay, you can see that in the part of the halo stars, they tend to flat out at the value of roughly -0.2, which is roughly the same as for our object. So we could expect that this source, having roughly 20 Jupiter mass, has formed most probably similar to stars in the halo. Okay, so this is still an ongoing work. I did not mention the part of the MIRI spectroscopy, which was taken a bit later than those observations. And in this range that MIRI has covered, around 11 microns, we expect to see another feature, another absorption line from silane. So this could verify or confirm that this is indeed caused by this molecule. Unfortunately, I won't be able to show this today, but I can just tell that we are starting to analyze this data, and we really see some absorption feature present at this location there. But it could be mixed with other expected molecules, so it's about a little bit tricky to definitely say whether it's this or that. But in any case, these studies are quite good guide for the forthcoming studies of other very low temperature substellar objects. So we don't know whether this particular object is simply a lone outlier, one example of a specimen of a previously undetected population, or what is the rate of substellar content in the Milky Way halo. well, this one we were able to observe it just because it is quite nearby. No, for the further ones, we cannot detect them in this way, at least. And another questions are whether this population of cool substellar objects, how far it can extend to planetary masses. No? Now we know quite a lot of examples of objects below the planetary mass that are single. So they were likely formed as stars, but much lower masses. And also, it's a good, let's say, laboratory place to study atmospheres and what are the roles of different variables and other than the temperature, than the mass. How does the metallicity, the gravity, and the age influence the observed properties of these objects? And well, just to be finishing, I would say that if you are starting now your career, your research, and you are interested in these kind of objects, I think it's a really exciting time to enter the field. I think because now we finally have tools to be able to study in great detail these very lowest temperatures objects. So just a few years back, we only could start to discover them and see the overall properties, the bulk properties. And now we are entering the phase where we can study in detail the chemistry and all the fancy processes that are occurring there. And here just to list several examples of discoveries done, I think exclusively using web data. So detection of things like deuterated methane or phosphines, isotopes, even emission, methane emission, which could be related to aurorae, and well, all variety of stuff. So finally, we can enter the let's say like a stellar astrophysics in the substellar domain. I think I will end here. Thank you. And if you have any questions, I'll be happy to answer. Thank you.
Question? Yes.
I have a question. Because you said that this object was more or less discovered by the accident.
By, sorry?
By the accident. Yes?
Yes.
Do you know about any plans to actually look for such object intentionally?
Oh, yes. In fact, this discovery was sort of by accident, because the person and the project that he was involved was in fact designed to discover cold brown dwarfs using WISE data. Let's say it was by chance, because in this case he was analyzing the field, checking other source. And by chance, he spotted that there is a something faint moving in the same field. So, but in fact, he was looking for cool brown dwarfs in that case.
Yes, Bartek, please.
So you mentioned like 10 different species that you analyzed, that you checked in order to verify which lines are from there. Can you check more? Maybe that's one question. The other is, can we see silane in like everyday life? Is it like in the rocks or something?
Wow. I think for the second question, I think it's like an industrial gas used in industry. I cannot tell you anything more from my head. But I think it's not like in the natural form. It's not abundant, I would say. And the question was, okay, if you checked other possible molecules, rather other than plotted here, yes. I think yes. I don't remember now which ones.
So there's probably a database of spectra that you
Of spectral lines, yeah, of this type of molecules, yeah. But in fact, there are not so many options to in reality that we could expect to be there. Well, if you don't consider something more complex.
Łukasz, you looks like the person.
You said that so what is the estimate for the mass of the
Right. So the mass that we obtained from retrieval analysis is 20 Jupiter mass. Yeah.
And you're sure about the parallax?
I would say yes. I would say yes. I would say yes. This is shown here.
It's almost as precise as Gaia.
Sorry, I will go back to this.
But I guess you also have the astronomy from James Webb.
No, yes, but the parallax that was measured here is mostly from Spitzer, I think. So it was quite accurate, I would say. And they also traced let's say the extremes, no?
Yes.
So the amplitude, they measured the amplitude.
WISE so great.
Yeah, that with WISE it would be less precise, no? But they follow up with.
Can you show the slide before?
Yeah.
There's a couple of bright stars.
Yes.
Because what you can consider is actual microlength by this object, the background stars.
This is one idea that we have with chemicals here.
Yeah, so
That will be
it's about 20 Jupiter masses, that's 16 barsides. Very quick calculations. It's an order of 1 millisecond, maybe less. And the time.
How much did you say? How much?
About 1 millisecond, maybe less. So it's
Okay, so we have to be very well aligned with any background.
Yeah. Yeah.
But it's a very yeah. This is for sure something worth checking. Whether let's say in the future, for example, no, it would align with something.
In the future, or you can look
Or in the past. Or in the past.
This is, when this is going 10 and 19, so data.
I mean,
will be doing 14, 19.
And in fact, the field is quite dense here.
Yeah.
Here. Well, maybe here it's not very well seen, but it's quite dense, relatively dense.
Yeah, you can increase the chance of seeing the signal by using more stars, especially repeating the Eddington's experiment. When the sun was lensing background stars. Right? So you do the same here, but you check multiple stars around it, you see the tiny displacement. And their data will have that information next year.
In the DR4.
Yeah.
Yeah, that would be very good. Something very useful because we will get the mass independently. Yeah.
At least you can put some constraints. If you don't see any signal, then that will give you a limit.
Well, the good thing here with the mass of this object, the good thing is that we were able to measure the bolometric luminosity. We know the distance quite well. The radius is well known because it's roughly the size of the Jupiter. So we could get almost directly temperature and the mass.
So you said it's 20, that was the uncertainty value.
Well, I'm surprised I didn't put it here. I think it's something plus minus 5, if I'm not wrong. Yeah, I will see if I have the paper here. Yeah, but in any case, it's rough, something like that. Plus minus 5. So I won't put it here. Yeah.
We have one question. We have any question from Zoom audience? I can see.